Hello and welcome to Mrs. Law's class. In this lesson, we're going to take a look at Venn diagrams and how they're used in probability. So to start off, let's take a look at the definition, mutually exclusive. So we say that events are mutually exclusive if they cannot occur at the same time. So that means that they share no common outcomes and are disjoint. So an example would be, let's say that we roll a die, then it is impossible for a die to be 5 or 6 at the same time or on the same roll. So that would be called mutually exclusive. So let's take a look at a couple of situations. Let's take a look at this Venn diagram on the right. So we have 4 dots in A, we have 3 dots in B, and then we have 6 dots here that are neither in A or B, but they're still inside this rectangle. So if each of the 13 outcomes is equally likely, let's use this Venn diagram to find the following probabilities. So the probability of A, we can see, is 4 out of 13 because there are 13 dots. The probability of dot being in B is 3 out of 13. And then the probability of choosing A or B would then be 7 out of 13. So we can have a dot in A or a dot in B. And then if we say that we want to choose a dot that's in that's in A and B, then that would be 0 out of 13 because there are no dots that are both in A and B. So the relationship between probability of A or B, probability of A plus the probability of B, is that we can say that the probability of A or B is equal to the probability of A plus the probability of B. And we don't have to worry about probability of A and B because there are no dots together. So in this situation, we would say that this is mutually exclusive. Let's now take a look at situation 2. All right, in situation 2, we have the circles A and B actually overlapping. So let's use the Venn diagram to answer the questions below. So there are still 13 outcomes which are equally likely. So the probability of A is still 4 out of 13 because there are 4 dots that are in the circle A. And then the probability of B, there are 5 dots, 4 that are exclusively in B, but then there's 1 that's in this joined part here. So there are 5 out of 13 possibilities of getting a B. And then the probability of A or B is we need to count all the dots that can be chosen from A or B. And that would be 8 altogether. We have 3 plus the 1 here plus 4 here. So there is 8 out of 13. And then the ones that are part of A and B, that's only 1. And that's that dot in the middle that is joined by the overlapping circles A and B. So that would be 1 out of 13. So again, let's write the relationship between these 4 probabilities. And we can see that the probability of A or B is equal to the probability of A plus the probability of B. And because when we add them together, we've actually double counted that one in the middle, we then actually have to subtract the probability of A and B. Sometimes in books or on websites, you might see a different notation called set notation. So we might see that A and B can be rewritten as A, and then with an upside down U, and then B. And then A or B is A with a proper U, and then B. So if we have a Venn diagram, and this is circle A and this is circle B, this middle part in here that would be A and, A with an upside down U and B. And then A or B would be all of this here, including the middle part. Let's take a look at a couple of examples. So one card is randomly drawn from a deck of 52 cards. So the following events are defined. So S is a card that is a spade, R is a card that is red, and F stands for a card that is a face card. So find the following. So which of the above three events are mutually exclusive? Well, these mutually exclusive events means that they cannot happen at the same time, or it's impossible to happen. So we can say that S, getting a spade card, is impossible with also getting a red card at the same time because spades are actually black. All right, next we have probably getting a spade. So we've done this before, and then that would be 13 out of 52, which equals a quarter. So a quarter of the cards are spades. Probably of red, well, half the cards are black and half of them are red. And D, probably getting a face card. So there are 12 face cards, Jack, Queen, and King. So that's 12 out of 52. And then reduce that to be 3 out of 13. All right, so now let's take a look at some combined events. So getting a spade and getting a red card. Well, those are mutually exclusive. So the probability of that happening is 0. Well, what about probably getting a spade card and a face card? Well, there are 3 spade cards that are also face cards. The Jack of Spades, the Queen of Spades, and the King of Spades. So there are 3 out of 52. All right, now let's contrast that with probability of getting a spade card or a red card. So it doesn't mean that they're happening at the same time this time. We want a spade or red. So we know that that's the probability of getting a spade card plus the probability of getting a red card. So probably getting a spade, we found out from before, is 13 out of 52 or a quarter. And then probably getting a red card is a half. So a quarter plus a half is then 3/4. All right, and the last one here is probably getting a spade or a face card. So if I wrote this out using our formula from above, that would be the probability of getting a spade plus the probability of getting a face card, and then minus the probability of getting a spade and a face card. So probably getting a spade is 13 out of 52. And I'm not reducing because then it makes it easier to have the common denominator already. So plus, there are 12 face cards out of 52. And then we found from before that there are spade face cards. So we're going to minus 3 out of 52. And when we do all of that, we get 22 out of 52, which equals 11 out of 26. All right, let's take a look at our second example. So there are 30 students in a class. 16 students surf the internet, 10 students check email, and 6 students do both. So what's the probability that a randomly selected student in the class surfs the internet or checks email? So if we draw a Venn diagram of this, I'm going to draw a rectangle, and I'm going to draw my 2 circles. And I'll say that this circle is internet, and then this circle is checks email. So we always start with the middle part where the overlap is. So we know that 6 students do both. So we're going to put 6 in the overlapping part. And then we can go back to read the rest of the sentence. So 6 students surf the internet. So since 16 surf the internet, 6 are already counted for in the middle. So therefore, 16 minus 6 is 10 for this left part, where they only surf the internet. And then 10 students check email. So those 10 students include the 6 that are already in the middle part here. So 4, 10 minus 6, 4 exclusively only check email. So now we have 10 plus 6 plus 4, so that's 20 students. And we still have 10 more students because there are 30 students in the class. So I'm going to put 10 on the outside. So the probability of internet or email, if we use the formula, that would be the probability of using the internet plus the probability of using email minus the probability of those students using internet and email, because we're going to double count. Now, if we just take a look at the Venn diagram, we can see that the probability of those using internet or email would be the 10 plus the 6 plus the 4, which equals 20 out of 30. Now, if we choose not to use the Venn diagram and we just choose to use the numbers in the problem, probably using internet would be 16 out of 30. Those using email would be 10 out of 30. And then we minus those that are using internet and the email, which would be 6 out of 30. And by doing it this way, we get 20 out of 30 as well. And that reduces to 2/3. So that's how we can use a Venn diagram to help us do probabilities without actually having to use the formula every time. But if you would like to use the formula, you can do that as well.